Greetings and welcome to another exciting lecture in geomorphology. Today we're going to be continuing our exploration of river channels and fluvial geomorphology, and we're going to move on to the exciting topic, which is channel patterns. So we'll be talking about the different ways that we classify channels, the shape of the channels, and then relate that back to the river function and how rivers are effectively moving sediment. And so we will kind of explore that intersection between the sediment in a channel, how that channel looks in terms of the morphology, and then tie that back to the river trying to move that sediment. So that's our goal for today. The picture you're looking at here is from Yellowstone National Park and the Gallatin River, where I've had students looking at trying to understand better the morphology of channels and the climatic controls on the channels and the form of the channels and sediment transport in the channels. So that's what we're looking at here. And in this case, what we're looking at is students using an RTK GPS. And what they're doing is they're measuring the channel morphology right now. And so by doing these types of measurements, we can start to understand a little bit more about the channel and how it functions. Okay, moving forward. When we start to quantify and characterize the morphology of the channel, one of the first variables we have to understand is something called channel sinuosity. And channel sinuosity is essentially a measure of how curvy the channel is. So sinuous. Is that channel very straight, or is that channel highly curved as it goes back and forth down the valley floor? And so here, how we actually measure channel sinuosity is by taking the length of the channel and then dividing it by the length of the valley. So here I've got my channel, the actual channel itself, so we can measure that length with all those curves, those meanders going all the way up and around. There we go. So that would be our channel length. And then we just divide that by our basically a straight line down the valley, that valley length. And that allows us to start to say whether a channel has lots of these curves or if it's relatively straight. The other characteristic of kind of the sinuosity of the channel that we measure is something called the geometry of a meander. And so the geometry of the meander is going to tell us a little bit more about this form. Whoop, here we go. Better. About this form of the channel right here. How big are these meanders, these curves? How tight are they? And so two things we'll talk about is the wavelength. So we'll measure the wavelength between meanders as it goes across the valley. And then the other one here is the amplitude of the wave. So is that channel, are those meanders going all the way across the valley? Or are they kind of pinned to one side of the valley? Another thing we can actually measure is the radius of curvature, kind of how curved are these meander bends. So we'll use those to characterize these different types of channels. Okay, so with this kind of understanding of kind of the meandering nature of streams, the sinuous nature of streams, we first will define streams that are very straight, and we call these straight channels. Straight channels have low sinuosity, values less than 1. And remember that channel sinuosity can't be lower than 1 because a perfectly straight channel would have the valley width, have the channel length divided by the valley length and be perfectly straight. So that would be a straight channel. And then a meandering channel would be a stream that has a sinuosity greater than about 1.5. And I know you're asking, well, what about the middle there? Yeah, these are kind of boundaries that we put on channels, right? That when we're close to these values, you can either classify it as straight or meandering. So this again would be a meandering channel right here. Okay, two other channel morphologies we have to discuss involve multi-threaded channels. When you have a channel that is active with flow in two separate locations. And so there's two ways that we describe these. The first here is what we call a braided channel. And so a braided channel are going to have unvegetated islands in them. And then we call this a braided channel. And braided channels, we generally, because there's no vegetation on these, we think of these as unstable parts of the landscape, that the locations of these islands is changing over time, so the vegetation can't colonize those islands and stabilize them. The other type of channel right here is what we call an anastomosing. An anastomosing channel is where we have multi-threaded flow and we have vegetated islands. And so when you have vegetated islands, we think of these channels as stabilized and more permanent than a braided channel. And so here's a picture kind of showing just a multi-threaded channel, and we can think of these multi-threads as being relatively stable in time, especially compared to these braided channels. Okay, so here's kind of an image of one of these. This is from Vermont, and this is the Otter Creek in Vermont, and we're looking at a relatively low sinuosity straight channel here. Compare that to this picture from Slough Creek in Yellowstone National Park, where we have a very, very sinuous channel here. Look at this big meander and big sinuosity down here. And I think you can see some evidence of some older sinuosity here on the side. We'll talk about that towards the end of the lecture today. Okay, here's a picture of a braided channel. The braided channel, notice all these multi-threads here of the channel, and notice there's not a lot of vegetation on these islands, suggesting to us that the stability of these is very low, that these islands are actively moving and the channels are shifting back and forth across the floodplain. So this is from the Resurrection River in Alaska. And this should clue you in a little bit to where we often find braided channels. We find them in relatively steep mountain environments where we have a lot of sediment supply. So you can think about a braided channel as essentially choking in its own sediment, and it's kind of just so filled up that the stream is just kind of flipping back and forth as it's trying to move all this vegetation downstream, all this sediment downstream. Okay, here's a bar braided channel here from New Zealand. And these are generally high sediment load streams as well. But notice that we have vegetation here. So with that, we can think of these islands as slightly more fixed in time relative to those braided channels. So bar braided island, this is that anastomosing channel. I should have written anastomosing. How about if I write it on big A for anastomosing? There we go. Okay. Another interesting thing we can do is characterize our channels and these different morphologies based on both the size of the river and also, and by size I mean the discharge of the river and also the valley gradient. And so this is a neat way to think about how we have different channels. So what we're looking at here on our x-axis, we have the valley gradient going from 10 to 1 to 10 to the negative 5. So this is low gradient. Down here, then these would be higher gradient channels here. Okay, and then we have median annual flood. So what we're looking at here is essentially discharge from large to small. Okay, how we can interpret this graphic is if we think about a river at a particular slope. So let's just take an average slope here of 10 to the negative 3.001. If we think about that valley slope, what we see is that as our rivers become larger at these slopes, we transition from meandering channels to what are called transitional channels up to these braided channels. And so what that's suggesting that as we have bigger rivers with higher discharges, we're more likely to create braided channels, and because of that, these braided channels are probably related to sediment supply. And in these settings where we have high discharges, we're able to move more sediment, and so we have that sediment that's filling up the channels and created that multi-threaded pattern. Also notice that we generally see our anastomosing channels at the highest flood discharges and the lowest gradient. So again, think about that. We've got high discharges, so we've got lots of sediment supply, but we've got relatively low, well, here, let me point over here now. We've got relatively high discharge, so up here, but we've got relatively low gradients, and so we have less erosive potential of the stream, and we're able to vegetate those islands. So this is a really nice way to think about how a river and its form is related to both the size of the river in terms of discharge and the slope of a river. Okay, Our next way that we classify channels, moving beyond pattern, is what we call channel reach morphology. Now, a channel reach is just a section of a river. And so reaches, it's up to you to kind of define the length over which you're declaring a reach, but we're talking anywhere from, tens to hundreds of meters, maybe a kilometer. That's kind of the scale we're thinking about when we're thinking about the reach. And so what we see is we see a consistent change in the reach morphology as we go from the top of the drainage basin. So notice here we've seen this before, right? We've seen the hill slopes colluvial systems, and we're not going to talk about those today. We've already done that. But as we move into the fluvial portion of the spectrum here of the drainage basin, we see a consistent change from cascade pools to step pools to plain bed to dune ripple all the way over here. So when we think about this, these are the terms we're going to be looking at here in terms of the morphology of the stream. A cascade that we see at steep rivers. As we starting to have a little bit less steep rivers, those will be step pools. As we move on to the flat valley floors, we'll have more plain bed, pool riffles, and finally dune ripples. So this is all part of the fluvial part of the system we're talking about here, right? This is the fluvial part, the channel morphology. And what we generally see is that we see a consistent change in the sediment supply, the channel slope, and the channel roughness as we move down the fluvial network. And so at the top of the drainage basin in our steep mountainous terrain, this is where our sediment supply is generally low. We have high channel slopes, so high channel slope, low sediment supply, and very, very rough channels. These are what we call supply limited channels, that the stream is not effectively able to move a lot of the sediment and so or material in the valley floor, in the channel, and so we're not really able to move that sediment down. As we move down the channel, our channel slopes decrease. We're able, as our streams get larger, we're able to have more discharge, more shear stress, and move more sediment, so our sediment supply goes up. We generally see our roughness go down as we get smaller and smaller material, as we get more weathering and breakdown of material and erosion in the channel that makes smaller pieces of material. And we transition from supply limited to transport limited systems. And so in transport limited, again, we're starting to choke up our valley floors and our channels with sediment, and we're only moving as much sediment as our discharges will allow, but there's plenty of sediment there. Okay, so let's look at some pictures of what these look like. We go down the channel. So up in the steep mountain terrain, we get what are called the cascade morphology channels. I like this. This is a figure from your textbook. Notice that we can look at a picture, the plan view here looking down on the channel, and then our cross-section view as well. And so in our cascade, we basically have giant boulders, and our stream is cascading down over these big boulders. And if you look here, look at the size of some of these boulders. You guys seeing these? Boulder, boulder, boulder. Does this look like a stream that can transport these boulders with any frequency? No, I totally agree with you. Probably not. And the reason for that is probably these are related to debris flows. Some of these big boulders might be related to debris flows coming from the mountain, from the sides of the valley. They might be related to rockfall coming in. And so our channel isn't able to effectively move this big stuff. And essentially our stream is superimposed on these really, really big boulders. And so you might not have a lot of spacing in where these boulders are because you're not able to effectively move these boulders in the river itself. So we call this a cascade morphology. Think really steep mountainous terrain is where we have cascade. Okay, moving down, we develop what's called a step pool morphology. And in a step pool morphology, we'll see some organization now within the channel. And so the river has the ability to move the sediment to some degree and develop essentially a steep step. And so the step right here is a high slope. And then next, between the steps, we have the pools. And the pools are finer grained, flat, relatively flat parts of the channel. So again, this is great swimming hole country right up here. So you want to hop in the pools here in between the steps and maybe even jump off the steps into the pools. So this is a step pool morphology, still associated with relatively steep mountainous terrain where we're transporting large boulders down into the channel. Some of these boulders might be so big that they're really not moved effectively in flow, but we are able to transport the fines, and we're able to develop kind of, these pools in between the steps. Okay, as we move down our drainage basin, we'll come across next what's called plain bed morphology. And so plain bed morphology is kind of boring. You just basically have essentially, a consistent gradient down the channel, reach to reach, with relatively the same size material. You might get a couple of large boulders here and there, but for the most part, we get a linear down gradient movement of the channel. And we see that the channel is consistent in terms of its the size of the material on the bed. So we call this plain bed. The picture you're looking at here, this is from the Snake River in Wyoming. So plain bed morphology. Here, basically the channels are large enough that we're transporting basically most of the stuff in the channel. The river is able to move and transport. Okay, as we move down a little bit farther down the system, we'll create what is called a pool riffle system. And a pool riffle is a relatively lower channel gradients. And here we're able to develop essentially our channels that have a pool with a steep section, and then a riffle, below that, which is the steep gradient part. So the pools are kind of form this kind of scallop depression in the channel, and then the water surface stays over the top of that, and then on the steep side of that scallop depression is the riffle going down to the next channel. So here we've got a river here, and notice the flat water up here. That's the pool part, and then as we get a steepening over the riffle, we get shallower water, and you can see that little bit of turbulence on the top there. So here's our pool back there, and then here's our riffle down here. Pool riffle morphology. This is from Glade Creek in between Teton and Yellowstone National Parks. Okay, all the way down our system at relatively low gradient portions of the stream are where we have dune ripple channels. In dune ripple channels, we have abundant sediment supply. We're kind of choked in sediment, and the morphology of the channel is now a function of those sedimentological features that we talked about in fluvial processes. So we talked about, depending on flow depth and velocity, we'll develop a ripple and dune sediment structures in the channel. Well, the dune ripple morphology right here, this dune ripple, represents the movement of dunes and potentially anti-dunes along the channel bed. So these are relatively low gradient where we have abundant sediment supply and high discharges, and we're kind of moving that sediment in ripples and dunes down the channel. Okay, that's a good enough job there on our channel morphology. We talked about patterns and then kind of a reach scale morphology. Let's talk about one more thing today, and that is floodplains. So the last part we need to talk about here is kind of the morphology of the channel and associated with a river that floods. So a floodplain, by definition, is connected to the channel by frequent flooding. And we can talk about what frequent means, but oftentimes when we define the floodplain, we're talking about the portion of the channel that gets flooded roughly every 1.5 years in terms of our frequency. So the floodplain is the flat part of the valley floor that we expect frequent flooding. And so because of that, you're going to get low velocity waters as the channel as the water spills out of the channel and onto the floodplain. And so as you slow the water velocity down, you decrease shear stress, you decrease your ability to effectively move sediment, and you dump fine-grained material onto the floodplain, which makes floodplains very fertile agricultural locations because of all that fine-grained material that's nutrient-rich that is getting dumped on those valley floors. So here's someone scooping up some of that recent deposition floodplain material in their front yard here. Okay. So when we think about a channel and when it leaves its banks, that's when we've got a flood. A channel is, water is confined to the channel, everything's happy. All of a sudden, as our discharge increases, it spills off out of the channel, and that's a bank. We've got a bank full flood, and then once you reach that bank full discharge, once you spill out onto the margins of the channel, we call that a flood. Now, interestingly, right at the channel margin, that's where your stream is first going to lose power, right? It's going to lose shear stress because you go from really thick water in the channel to very thin water as you're spilling out. And so because of that, you'll preferentially deposit sediment right along the margins of the channel. And so because of that preferential deposition, we develop these little hills next to the channels called levees. And so levees develop right on the margins of the channels. These are natural features that essentially serve to kind of keep the channel, the river water in the channel. Now, interestingly, we kind of like that. And so oftentimes we'll reinforce levees with more sediment to keep a channel from flooding. The levees are natural, but then we will stack them up even higher and make sure they're connected downstream so that we can prevent the area outside the channel from flooding. Oftentimes, next to the channel, we'll have kind of low elevations on the other side of the levee, and we can make little swamps back here because you'll have groundwater flow connecting the stream. Sometimes on these valley floors, you'll have a small little channel flowing along the side. We call these yazoo channels. Okay. So this is kind of a schemagram here of what this is. You've got the suspended sediment moving in the channel. As we enter flood stage, that water spills out onto the floodplain. We have that relatively low thickness of water here, decreased shear stress, and we deposit sediment and stack sediment up on our floodplains. And the problem then becomes that we often will build on the floodplains because they're flat, and so we end up with floodplain deposition in our house. So here's a river flooding its floodplain. You can see the natural levees. And when these are not reinforced, a levee will oftentimes be breached and you flood across the floodplain. Naturally, these things don't necessarily always confine the river to the channel. They just preferentially have been created because you dump sediment right on the margins of the channels. All right, let's watch a little animation here of how these processes work. So flood and levee development. All right, so here we are flooding across the channel, dumping that sediment, and we dump our sediments out. All right, let's watch that again. There it is dumping out. All right, let's click in here and look at levee development in detail. So we can see how over time you preferentially dump material right on the margins of the channels and preferentially build up your levees on the side. Okay, moving on. Another key characteristic of channels, especially meandering channels, is that they're not fixed in time. They migrate back and forth through the floodplain through what we call channel migration. So as a channel migrates, we develop an erosional area that we call the cut bank. So here's a couple of cut banks here. Cut banks here, cut banks here. And then on the opposite side of the cut bank, we've got the point bar. And so the point bar is where you're depositing sediment. The cut bank is where you're eroding sediment as that channel kind of fire hoses back and forth across the valley. Oops, sorry. Okay, and then, sorry, I just wanted to point out, here's a picture with some real nice meanders, and then you can see some older meanders on the side here, some abandoned meanders. So, some more terms here. Here's our meandering river flowing down with a highly sinuous river. Right here, these are the point bars, and then so we're depositing sediment as the stream is migrating, and then we're eroding sediment on the other side on the cut bank. And same here. We're expanding on the meanders on the point bar, and we are cutting on cut bank. If we look at a cross section, so here's a cross section right here. So this is a cross section. What we see is that we have lower gradient portions of the channel on the point bar side. So we have less deep water. And so because of that, we'll preferentially deposit sediment on the point bar. And then we have a steep section on the on the other side of the channel, and so we have deeper water, and we get this kind of kind of uh, channel flow that kind of moves in this circle here, that essentially will scour the cut bank, and so the cut banks are preferentially scoured as we develop kind of this kind of pattern of flow in the channel. Okay, so we can kind of watch a little video here over time. Our point bars forming at the expense of our cut banks. Oftentimes what happens is your channel will meet and you'll cut off a meander neck, and that will create a cutoff, and on the other side of the cutoff we form what's called oxbow lake. Oxbow lake or a cutoff meander lake. So here's a meandering channel here on Slough Creek, and then look at all of these essentially oxbow lakes. These are all small little abandoned meanders as the stream has meandered back and forth across the floodplain. So point bars, oftentimes you can identify the point bars because they don't have much sediment on or vegetation on them because they're relatively new. And then our cut banks on the other side. Here's an example showing the main channel right here. This is our main channel. And what we've seen is that this stream has become so sinuous that we're cutting off those meander necks and creating a steeper path down the stream. And so when we do that, basically the stream is able to kind of just cut down across that meander neck and save a bunch of energy by going straight down. Okay, let's watch a little animation of how this all works. So let's kind of watch meandering streams in time. So here's our stream meandering across and widening its floodplain along the valley floor over time with point bars and cut banks. Once in a while you get one of these oxbow lakes that form. We've got our cut banks and our point bars. Kind of look here a little bit more detail at our creation of an oxbow lake. So over time, more and more erosion in the newly formed channel, and then we'll get depositions on the margins of the channel right here, and then we will cut off that meander and create a what's called a meander scar, and then if it's filled with water, an oxbow lake. So we can watch this in river systems over time and kind of see how these cutoffs form. So here's the Mississippi River. And notice this white stuff right here on this meander neck. So here's the big meander in the river as the stream's going down and around. Right here, this is fresh sediment that was dumped after the 1993 Mississippi River flood. And so over time, we will have potentially more erosion of the meander neck and cutting off right here on our cut banks, and this will become the primary channel, and we'll abandon this big meander here. Keep your eye out for meanders. This is going to be really, really important for understanding our next lecture, which is going to be The Control of Nature by John McPhee and the Atchafalaya River. But what this image here is just showing is kind of mapping of different meanders and different channels of the Mississippi River over time. And I don't know if you can see this, but the blue values here are where the stream was in the 1760s. So all these areas in blue here. And then the red is from the 1820s. So here's some old meanders here. And then the green is from the 1880s. And so we can kind of track how a river meanders across its floodplain over time. This can lead to some fun geographical anomalies. And so here we're looking at Carter Lake in Iowa. And so where we are is on the Iowa-Nebraska border. And the border between Iowa and Nebraska is the Missouri River. So here's the Missouri River flowing down. Now, what the Missouri River used to do was flow along this big, huge meander. So because of that, essentially Carter Lake, Iowa, this town in Iowa, was, video went off, let me pop it right back on. And we're back. Okay, we're back. So Carter Lake right here used to be able to just drive across the meander neck into Carter Lake. If you're right here, drive right in. What happened was we eroded that meander neck, and now the Missouri River has cut off this big meander. And now if you are in the state of Iowa, and you want to get to Carter Lake, you have to cross the Missouri River. And so Carter Lake, Iowa is a little island of Iowa in Nebraska. Okay, one final term I want to know is the term of an avulsion. And so avulsions occur where you're going to basically have your channel jump from one stream to another. And so an avulsion occurs, the channel's flowing down in one meandering path and then it jumps to another. I'll show you a great example of this. Here's an avulsion from the Gardner River in Yellowstone, Montana. As everyone see here, here's the main flow of the Gardner River flowing down in this meandering pattern down here. But does everyone see what looks like a pretty decent sized channel over here? This used to be the main channel of the Gardner River, and we've had an avulsion where this is cut off this section of the river and created a new channel. And so notice here on the map, this is a map of the Gardner River, and it shows the Gardner River on the other side of the valley. And what's happened is we've cut off a bunch of those meanders, and we call that an avulsion. So is everyone clear on that? The stream, basically, it's not a single meander cut off. We've cut off multiple meanders. And as we do that, we call that an avulsion. The channel has jumped, the river's jumped from one channel to another across the valley floor. We call that a channel avulsion. Okay, that's all I've got for you on channels. Thanks so much for watching. We'll be back next time, and we'll be talking about the case of the Atchafalaya River down on the Mississippi in the southeastern United States. So keep on the lookout for that. Thank you so much for watching today. Have a wonderful day, and we'll see you soon. Bye.